Hello, welcome to Team 4's final video report for Virginia Tech's Embedded System Design course for Spring 2016. Team 4 includes Brooke Taylor, John Marshall, Bryant Sweet, and me, Daniel Neel. We will begin this video by explaining the general goal and purpose of this project in a nutshell. The project takes place on a 3-foot by 3-foot field, where two rovers are charged with picking up a variable number of tokens while avoiding any obstacles present. A standalone sensor network scans the field to determine obstacle and rover locations. This information is relayed to a central coordinator, which determines a search path covering the entire open area of the field and sends appropriate movement commands to the lead rover. While the lead is told how to move, the follower rover must use its sensors to determine its own movements in order to adhere to the lead rover's path as accurately as possible. When the lead rover comes across a token, it immediately tells the coordinator, which then informs the follower rover. Next, the follower moves to the token and picks it up in some capacity before sending back a confirmation. When all tokens have been found, the demonstration is complete and the rovers stop moving. Before we proceed, let's quickly address the communication system, one of the foundations of the integrated project. The system's components send information via Wi-Fi modules connected to a Raspberry Pi hub. Generally, messages from the rovers and sensor array are relayed to the coordinator, and the coordinator sends information and commands to the appropriate component. We used a 10-byte message format, which included 1 byte each for the start and stop delimiters, 1 byte to indicate message type so it can be acted on appropriately. Another byte, acting as an iterated sequence count, allowed us to determine if messages were lost in transit, and the remaining 6 bytes stored data. For consistency and ease of integration, all messages in the system followed this format.
The basic function of the lead rover is to accept movement commands from the coordinator via a wireless communication device. The lead rover will also use this device to send important signals back to the coordinator. After completely executing the movement commands, the lead rover will then send a signal back to the coordinator to indicate that it has finished the movement command instructions. The purpose of this signal is to indicate when the lead rover is ready to accept another movement command. The movement commands consist of forward movements with a specified distance in centimeters. The lead rover is also able to make turns of a specified angle in either the left or right direction as determined by the coordinator. The lead rover contains 4 IR emitters which are used to send out 4 signals in the cardinal directions. These signals are used by the follower rover to determine the direction it must travel in order to reach the lead rover. The lead rover utilizes a reflected sensor array facing downwards in order to detect tokens which are a different color than the roving surface. Upon token detection, the lead rover will send a different signal to the coordinator indicating when it has found a token, since the lead rover is unaware of its own current location within the field.
The follower and lead rovers share some fundamental design elements involving movement basics. Pulse width modulation, or PWM, is a key technique used for motor control within these rovers. PWM involves adjusting the duty cycle of a digital signal, the proportion of time the signal is held high within its period, at a specified signal frequency. The longer the signal is high, the more power is supplied from the pin to the corresponding motor, and the faster the rotations of the rover's wheels. Pulse width modulation allowed us to control the rotational velocity of the rover's treads to help meet the project's needs, and it was similarly used to control the servos of the sensor array. However, this alone could not guarantee equivalence between the two treads or consistency in speed on different terrains. To address that issue, we had to read the motor's encoders, which signal high several dozen times as the motor rotates the wheel. While the rover is moving, the encoders trigger quite often, so tying them to interrupts in the code would be inefficient. Instead, we connected them as external clock sources. Our microprocessor has several clocks which can effectively be used as counters, and we read the number of encoder ticks that were tallied every 100 milliseconds. Through testing, we determined the conversion between an encoder tick and measurable distance in centimeters, and dividing this by 1/10 of a second allows us to find the rover's current speed. This information was useful, but we still required a way to quickly and accurately adjust the PWM to maintain the desired speed. Here, a PID algorithm was implemented. A proportional integral derivative controller uses the previous output of a system to adjust for error. It does this by incorporating the results of 3 components, each with a specified coefficient. The proportional term uses the error between the last output and the ideal, and it is usually the most influential factor. The integral term accounts for past error in the system. If previous changes did not solve the error, the magnitude of this term continues to grow for each iteration. The derivative term is used to predict future errors based on the rate of change of the current error and prevent them from happening. Using a PID controller to determine the PWM output for each motor gave us the means to more accurately control rotation through the relative speeds of the left and right treads, as well as the ability to adapt and meet the desired velocity on different surfaces. Now, where the lead rover is designed to use these algorithms to do what is commanded of it by the coordinator, the follower rover has to determine its own independent actions. It accomplishes this with the help of 2 forward-facing IR distance sensors and 4 IR receivers pointed horizontally in the cardinal directions. As they intercept the lead's emitted IR signals, the receivers help identify the lead's relative direction. Once the follower is oriented toward the lead, its upper sensors report the target's front distance, with accurate readings up to 30 centimeters and reliable identification to around 40 centimeters. In general, the follower backs up if it reports an object within 5 centimeters of its front edge, and it remains stationary if the lead rover is positioned 6 to 7 centimeters away. The rover's state machine remains in a follow state while both distance sensors report a target. When one loses the lead, it begins counting the number of consecutive sensor readings. If the second sensor does not lose the lead within a predefined number of readings, rover trajectory is simply skewed, and it rotates to fix its orientation. If the remaining sensor loses the target quickly, however, the lead has taken a sharp turn. The follower tracks the lead's last known location, moving forward the magnitude of the last reliable distance reading in terms of encoder tick count. Next, the IR receivers are used to determine which direction to rotate in order to reacquire the lead. In this way, rather than simply tracking its target, the follower actually mimics the lead rover's path. Token finding behaves similarly. When a token message is received via Wi-Fi from the coordinator, the follower saves the distance to the lead rover as soon as its sensors have it targeted. This location gains top priority, and when the follower is positioned over it, it signals to the coordinator that a token has been picked up while flashing an onboard LED for visual confirmation.
The sensor array consists of 4 towers, each containing 2 infrared distance sensors. One distance sensor is on the lower level and is used to detect obstacles. The other distance sensor is mounted about 10 inches higher and is used to detect the lead rover. Because of the multi-layer design, the top distance sensor will detect obstacles and allows the sensor network to detect the lead rover among many obstacles. These 2 sensors are then mounted on top of a servo that will allow it to pan one quadrant of the field. The readings of the 4 sensors are then used to calculate the center points of all the objects on the field. It is then sent to the coordinator.
In the beginning of the simulation, the coordinator is responsible for kicking things off by having the sensor network take in and store object data prior to the rovers being on the field. The coordinator will then give the follower rover a start signal. The coordinator receives sensor data that details where objects are, as well as the lead rover. Using this information, the coordinator can instruct the lead rover on when it needs to turn and how far forwards it can move. Once the lead rover moves and tells the coordinator it has finished executing its commands, the coordinator will instruct the sensor network to take a new reading. The coordinator then compares the new reading to the previous data it has stored to tell the lead rover what to do next. Another responsibility of the coordinator is to keep track of the number of tokens on the field. This number is set at the start of the demonstration and is decremented anytime the follower rover indicates it has picked up a token. Once all the tokens have been located, the lead rover will send the follower rover a stop signal, thus completing the simulation.
The startup sequence in our demonstration was unique. Since the sensor network could not detect the orientation of the lead rover, it was necessary to design a special startup sequence that would enable the coordinator to determine the lead rover's orientation. The first step in this sequence was to have the sensor network scan the field without any rovers present, as shown in this picture. After this, the rovers are placed on the field and the follower is giving a start signal and aligns itself with the lead rover. Then the sensor network records the starting location of the lead rover, which is then instructed to move forward by 30 centimeters. The sensor network then sends the lead rover's new position to the coordinator, and the difference between these two positions is used to calculate the orientation of the lead rover. After this sequence is completed, the lead rover begins to traverse the field searching for tokens and avoiding obstacles as shown in this video.
The following section will discuss the operating environment and reliability of the integrated system. At the beginning of the design phase, we had some concerns about interference between similar IR sensors when they were pointing directly at each other. It turned out that this wasn't a problem and we were able to receive accurate data in all situations. We also needed an open area that was well away from walls such that the follower could focus on finding the lead rover without interference. However, we did discover that ambient light can have some effect on the infrared sensors. We found out that exposure to direct sunlight will cause erratic readings. For our IR sensors, it was necessary to operate under iridescent lights in the embedded lab for accurate readings. Another key aspect of system reliability involves stable communication. Initially, we had issues with the Wi-Fi modules not receiving every message that was sent. To address this problem, we implemented handshaking with all of the important message types so that if the receiving Wi-Fi module failed to acknowledge a message, the transmitting Wi-Fi would keep sending that same message until it received a response. Some of the important message types that we use handshaking for include the token finding sequence between lead rover, coordinator, and follower rover. This was important because we didn't want to miss a token or double count the same token during different points in the field traversal because of errors in the Wi-Fi network. Additionally, all of the messages between the sensor and coordinator required handshaking. This was to make sure that the coordinator received all of the sensor information accurately.
Through the completion of this project, we have come to realize several improvements that could have been implemented for a more stable design. For example, in the weeks leading up to the final demonstration, 3 out of 4 of the servos for the sensor network failed. We suspect this is because we purchased inexpensive servo motors, which had insufficient lifetime for the length of this project. We were using them in a way that they were not intended for, which is panning 90 degrees as fast as their motors would allow, for hours at a time. For future projects, we will try to match the type of servo to its intended use cases and invest in reliable motors. The most unique element about our design was the multi-layer design approach. Specifically, we designed the obstacles and follower rovers to be shorter in height than the lead rover. However, we found that sometimes the sensor network detected the follower rover because of the infrared sensors protruding slightly into the upper layer. One improvement that we could have made to help the sensor network find the lead rover was to further increase the height of the upper level of sensors. This would also require that we increase the height of the structure on top of the lead rover. If we had implemented this change, there would have been fewer errors in the sensor network because there would not have been any interference from the follower.
The follower rover could be improved as well. Due to the limited angle of the IR emitters and receivers on the 2 rovers, there are dead zones where the follower does not actively know the direction of the lead. Placing IR components in the corner for 8-way readings would generally cover these at the cost of added software complexity. Additionally, the follower could be made more robust by adding a second PID algorithm specifically for following distance. This would allow the rover to quickly adapt to any changes in the lead's movement speed and further reduce chance of collision. And this concludes our project presentation. We learned a lot this semester, partially from our successes, but especially from our mistakes. Planning is vital, communication is key, and any change made to the system should be tested as soon as possible. Thank you for watching.